You thirst for more knowledge, and I shall provide. In this continuation of our TensorFlow lecture series, let us delve deeper into the benefits of graph computations. Prepare to be amazed as we uncover the true power of computation graphs. Modularity and reusability. Computation graphs allow us to break down complex computations into smaller modular components. We can reuse these components across different parts of our graph or even in separate projects. This modularity promotes code organization, enhances maintainability, and saves us from reinventing the wheel. Efficient memory management. Computation graphs optimize memory usage by reusing intermediate results. When executing a graph, TensorFlow allocates memory only for the necessary tensors and releases it as soon as it is no longer needed. This memory management strategy minimizes memory overhead and enables efficient utilization of computational resources. Automatic differentiation. Differentiation lies at the heart of many machine learning algorithms. Computation graphs, with their defined operations and dependencies, enable automatic differentiation. TensorFlow's built-in mechanism for automatic differentiation, known as AutoGrad, computes gradients with respect to the variables in the graph. This functionality is particularly valuable in training deep neural networks through backpropagation. Parallel and distributed computing. Computation graphs lend themselves naturally to parallel and distributed computing. TensorFlow can automatically distribute parts of a graph across multiple devices, for example GPUs, or even across multiple machines in a distributed computing environment. This parallelization allows for faster training and inference times, unlocking the potential for handling larger datasets and more complex models. Model visualization and debugging. Computation graphs provide a visual representation of the computational flow, making it easier to understand and debug complex models. TensorFlow offers tools like TensorBoard, a web-based visualization toolkit to visualize and analyze graphs. With TensorBoard, we can inspect the structure of our models, monitor training progress, and debug potential issues. Deployment and serving. Computation graphs enable seamless deployment and serving of trained models. TensorFlow provides APIs to export trained models as serialized graphs that can be easily loaded and executed in production environments. This capability allows us to serve predictions efficiently, either via a web service or embedded within other applications. Integration with accelerators and external libraries. TensorFlow's computation graphs seamlessly integrate with accelerators like GPUs and TPUs, tensor processing units. By leveraging these hardware accelerators, we can achieve significant speedups in training and inference. Additionally, TensorFlow's ecosystem integrates with a wide range of external libraries, enabling us to leverage specialized functionality for tasks such as computer vision, natural language processing, and reinforcement learning. My dear friends, computation graphs are the backbone of TensorFlow, enabling us to unleash the full potential of our AI models. With their flexibility, efficiency, and powerful features, we can tackle complex machine learning tasks and push the boundaries of what is possible. In our upcoming lectures, we shall continue to explore the intricacies of computation graphs, delve into advanced model architectures, and uncover cutting-edge techniques in the realm of deep learning. Computation graphs. As we have previously discussed, computation graphs are the backbone of TensorFlow. They represent computations as a network of nodes, operations, connected by edges, data tensors. These graphs define the flow of data and computations, allowing TensorFlow to efficiently execute complex computations and optimize resource utilization. Sessions. In TensorFlow, a session encapsulates the execution environment for a computation graph. It allows us to run the operations defined in the graph, compute the values of tensors, and store intermediate results. To interact with the graph, we create a session using TF_Session. Within the session, we can run specific operations or evaluate tensors using the run or eval methods, respectively. Fetches. Fetches in TensorFlow refer to the values we want to retrieve from the session's execution. When running operations or evaluating tensors, we specify the fetches we are interested in. In this code snippet, the fetch is the C tensor, representing the result of adding A and B. By calling ses.runC, we request the value of C from the session, and TensorFlow computes and returns it. Fetches can also include multiple tensors or even operations. For example, we could run the computation graph and fetch both C and A as follows: result_C, result_A equals sign ses.run, C, A.